before stars, planets, or galaxies existed. Imagine the universe compressed into an extraordinarily dense and compact state. In this proposed picture, geometry itself was tightly bound, and the passage of time may have been expressed very differently from the way we experience it today. Then came a dramatic transition. Energy and geometry began to spread outward in an event resembling the beginning of cosmic expansion. What had once been concentrated within an extremely small region started evolving into the vast universe we see around us. As expansion continued, the universe did not remain perfectly uniform. Small differences grew into larger structures. Matter and energy began collecting along enormous filaments, gradually forming a cosmic network stretching across unimaginable distances. Within this growing structure, vast clouds of gas gathered under their own interactions. Some regions became increasingly dense and turbulent. These enormous stellar nurseries would eventually become the birthplaces of the first generations of stars. In the GTEC hypothesis, some regions of the evolving geometry may form stable, knot-like structures. Different knots could represent different ways in which energy, information, and geometry become locally organized. It is an idea that would ultimately have to be tested against observation. Across the young cosmos, countless structures could form, interact, stabilize, or dissolve. Some may remain simple, while others become increasingly complex. From this perspective, the universe is not merely filled with objects. It is a continuously evolving geometric system. Inside dense clouds, gravity draws gas inward until pressure and temperature become extreme. Eventually, nuclear fusion begins. A new star is born, illuminating the surrounding gas and beginning a process that will transform the chemical composition of the universe. Around young stars, disks of gas, dust, ice, and rock begin to organize. Tiny particles collide and combine. Over millions of years, these structures can grow into asteroids, moons, planets, and complete planetary systems. But stars do not shine forever. Massive stars eventually exhaust their nuclear fuel and can collapse in catastrophic explosions. Supernovas scatter newly formed elements far into space, carrying the raw materials needed to build future stars, planets, oceans, and perhaps life itself. The material released by ancient stars becomes part of new generations of planetary systems. On some worlds, conditions may become stable enough for increasingly complex chemistry to emerge. The atoms inside living organisms were once created in stars that disappeared billions of years ago. Today, powerful telescopes allow us to observe light that has traveled across enormous distances. Looking deeper into space also means looking further into the past. Every distant galaxy becomes a record of an earlier stage in cosmic history. Modern astronomy does not rely on visible light alone. Radio waves, gravitational waves, high-energy radiation, neutrinos, and other signals can reveal different parts of the same cosmic story. Together, they allow us to test how the universe behaves across enormous scales. The central question behind GTEC is whether apparently different cosmic phenomena might share a deeper geometric origin. Instead of treating every mystery as completely separate, the framework asks whether common structural rules could connect them. Different observatories measure different signals, but all of them come from the same underlying universe. If a geometric theory is correct, its predictions should remain consistent across independent observations. Agreement must come from data, not simply from visual similarity. Weak gravitational lensing, galaxy structure, gravitational wave signals, stellar environments, and the cosmic microwave background provide possible testing grounds. Any proposed GTEC prediction must survive comparison with conventional physics, competing models, and real observational uncertainty. The universe clearly evolves from simple early conditions into increasingly complex structures. Geometry, matter, radiation, and time are deeply connected in modern physics. Whether GTEC can provide a deeper explanation remains an open scientific question requiring mathematics, simulation, and observation. If similar geometric signatures appeared independently across many cosmic systems, that would be significant, but a true unified theory must do more than connect ideas. It must produce precise predictions that can be measured, reproduced, and potentially proven wrong. Galaxies, stars, planets, and life are all parts of one continuous cosmic history. The elements in our bodies were forged through processes that began long before Earth existed. In that sense, the universe is not something separate from us. We are one of its consequences. One of the most speculative possibilities explored in this story is that cosmic expansion may not continue forever. If the large-scale geometry of the universe were eventually driven toward contraction, the cosmos could enter an entirely different phase, perhaps ending in a vast implosion. And if such a collapse could return the universe to an extremely compact state, perhaps another cycle could begin. Expansion, structure, stars, planets, life, collapse, and then renewal. This remains a hypothesis, not an established description of our universe, but science advances by turning possibilities into predictions and predictions into experiments.